apologize for last time for a small emergency that happened, but I knew I could count on Florin jumping in and introducing our, Philipp, who started on the second part of this short course on revenue management and platform. The last session was basically focusing on a single location with a quite interesting model that covers all the issues involved, and we'll continue from there, I guess. But one of the main output today will be looking also at multiple location, if I'm not mistaken.
You're right. Absolutely. So are we all set there? Okay, thank you, Victor. So all right. Can you see my screen?
I can see your dog, yes.
Excuse me?
See your dog.
Oh, you see? Okay, I guess something went wrong here. This shouldn't happen at this point anymore, right? Oh, screen one. Yeah, there we go. How about that?
Yeah, sounds right.
Great. Okay, so so last time we did not quite finish the slides. So let me first sort of do a quick recap and also a quick preview of what I plan to do today. And then I'll jump back to spend a few more minutes on this last model from last time, right? So, this was my very simple framework. Last session was focused on single locations. And we looked at models without spatial demand imbalances, right? In the most sort of the simplest model, there's actually no notion of space. So there can't be demand imbalances. There can be imbalance between the supply and demand, right? And so there the focus was on controlling demand through price and supply through wages. And if you look at time, because time is kind of the focus of a key feature in all these models, is that the cause of service delay is if all the suppliers are busy, and the mean delay, which customers care about, is increasing in the utilization. The model I did not quite finish, but we'll return to in a minute, is one where you do actually have multiple locations in some sense, but it's a very summarized, reduced form model without imbalances. So the space is kind of uniform, demand is uniform. And we did not really get into that yet, but essentially price controls demand, wage controls supply, and we can also control supply or the supply rate through the matching policy. So those are a couple of things that I will still get into in a couple minutes. The key thing is that from a time perspective, right, the cause of service delay in that model is there's a pickup time, a distance that comes from the distance between where the customer is and where the vehicle is or the driver is, right? And the mean delay is decreasing in the spatial density of idle drivers, right? So we'll come back to this in a minute. Just a quick preview of what I plan to do today. I'm going to look at fluid models in settings where we have spatial demand imbalances. And I'm actually going to talk about, my work joined with Maglaris and Lu, who I think is in the audience. I will probably not actually have time to talk about both things, but I think I should have time to talk about the first one, where you have a stationary demand imbalance. So think of it as there's a structural imbalance that lasts for maybe several hours during the morning rush hour or during the evening rush hour, where there's more demand going to a location than demand originating from that location, right? So on average, right, which is very different from the homogeneous space model. And there we'll look at the interplay between admission control to regulate demand and repositioning control to regulate supply. Time permitting, I will at least sort of give you a flavor of another model we're looking at, which I'm calling here non-stationary demand shock model. So think of this as it's a shorter time frame. You start in some sort of balanced state, but then there's a shock of demand at a hotspot. And this shock is not going to last for hours, right? So now you have, for the drivers that are not right there, they have to sort of figure out, should I bother to move there? And because the shock is not going to last forever, right, the delay for the drivers to get there and the risk of not getting there on time is a real concern, right? So there we're going to look at, or time permitting, look at wage-based supply repositioning control. So how can I set wages to give drivers an incentive to move to the hotspot and help me satisfy this lucrative demand that happens there, right? Now, before we resume the discussion here, right, let us jump back to this is where I was last time. I think the last slide was this one that I showed you, right? And really the key feature in this homogeneous space model is that the supply rate is not simply labor supply times a fixed service rate per server, right? Which is what we're used to in sort of classic queuing models. But so if you think of this from a classic queuing perspective, you can think of it as the service rate of available servers is state dependent, right? And the state dependence comes through the pickup time T, and the pickup time is a function of idle vehicles, right? And so last time, I think we ended on this graph where on the horizontal axis, you have, let's say, a trip supply rate, right? And on the vertical axis, you have the pickup time. So here, so think of it as, the supply curve has been put on its side here, right? But if the minimal pickup time, so here we're fixing the supply L, right? And we're seeing how does the labor supply L is fixed, and we're looking at how does the trip supply rate vary with the pickup time, right? So the shortest pickup time can be obtained if all the vehicles are idle, right? But of course, in this case, you don't have any supply rate because all the vehicles are idle. And then as the trip supply rate goes up, as the pickup time goes up, initially the supply rate goes up because now you have drivers that can, they can basically move to close by drivers, close by riders, right? As this happens, you have fewer idle vehicles, which means they tend to be on average further away from the riders. The pickup time goes up. And as the pickup time goes up, right, the service time becomes longer, right? And at some point, the system chokes or, reaches a maximum where you have such long pickup times that the trip supply rate is decreasing again, right? So this happens in this region here. And the last thing I think we did last time is to say, okay, so if you fix a given supply curve, right, you can sort of think of two possible ways of supplying a given rate of trips, what we call the good outcome, right, where the pickup times are relatively short, and the number of idle vehicles is, a little bit larger, versus the pickup times being somewhat longer and the number of idle vehicles being smaller, right? And this is what they call a wild goose chase, right?
Can you remind us capital Q? What is it?
Oh, the capital Q is meant to be the equilibrium trip supply rate, right? So think of, I mean, Q is kind of the common, think of quantity, right? And on this graph, you have the supply quantity and the demand quantity. And when they intersect, in this case, that would be like here, right? You have the equilibrium where the trip supply rate equals the trip demand rate. Make sense? Okay, so the couple of things I want to look at here is, you know, so a key point here is, you know, what happens if you misprice a little bit in this model. In other words, if the price, you know, if you drop if you're in this wild goose chase equilibrium, what happens if I vary the price kind of in the wrong direction? But before we do that, this is just another preliminary slide, which is, you know, if you fix the price, what are the equilibrium conditions? This goes back to Victor's question, right? The trip supply rate must equal the trip demand rate. So in the graph before, it's an intersection of the two curves. In addition, the labor supply has to be in equilibrium, meaning, so in, you know, the argument here is basically the earnings rate, where this is the price times what the drivers retain after paying the commission to the platform. And this here is the total quantity, which is evenly divided across everybody that's actually working, right? And this L is just an increasing function, right? So these are the conditions. And then there's just some technical results that say, okay, for any given price, there always is a stable equilibrium. There could be multiple ones, but if so, then the largest one would be stable, right? So this is just sort of preliminary result. So up to this point, we just assumed a fixed price, and then, you know, there's going to be a stable equilibrium, right? Now, this equilibrium could be in what is called a good outcome. Think of it here, we have a supply function, right? In this kind of bluish part, that would be a good equilibrium. If it's in the, you know, in this declining part here, the red part, like at point A, right, that is a wild goose chase equilibrium, right? So that equilibrium where you have sort of long pickup times and few idle vehicles, right? And so what is this proposition saying here? It's saying that if you start out at such an equilibrium, a price decrease is going to increase pickup times and decrease the number of trips, right? So typically you would think of, okay, I reduce the price, I get more volume, right? But here, because you're starting out in a, you know, in a very troublesome supply situation, right? You're going to actually end up with, you know, more demand that you have a hard time fulfilling because you have few idle vehicles and cars have to kind of do this wild goose chase to get actually to passengers, right? So long story short, it's going to have a very bad effect on pretty much every measure, right? Pickup times are higher, number of trips are lower, right? That means the number of drivers are working is also going to decrease, right? They get, you know, they get lower price per trip, right? And there's actually fewer trips to go around. Their surplus is going to go down, right? The revenue is going to go down. The welfare is going to go down, right? Now, for the riders, the effect is ambiguous because on the one hand, they pay less. On the other hand, they wait more because of longer pickup times, right? Just to illustrate here what happens, right? So think of this as being the initial equilibrium in this wild goose chase. If you drop the price, this is the initial demand curve, right? For any given T, this will increase the demand. So it goes to this dotted line here, right? So then sort of the short-term first order effect is you move from A to B, right? So basically you drop P, demand goes up, right? But because you're in this wild goose chase zone, you know, pickup times are also going to go up, right? As a result, the supply goes down and the quantity that you could supply also goes down, right? So this is sort of the first, like if you think of a dynamic adjustment, this is the first thing, right? But that's not in, that's, you know, now we need to see, well, what about the supply, right? So initially we're on this supply curve, think of it as L0, right? But now if you look at the drivers, right, they're looking at, there's a lower price and there's a lower quantity. And that means that their earnings are going to go down, right? And as a result of declining earnings, there's a lower labor supply, right? There's a low supply rate, and that in turn reduces the quantity and so on, right? And then so there's a sort of cycle going on until in this case here, right? The new equilibrium is here at sort of L infinity. I mean, of course, it's not going to be infinite, but it's just basically there's this cycle where labor goes down because it's less attractive to drive, right? So long story short, a small price reduction can have drastic adverse effects on performance, right? And so a price, so now we can say, okay, so we need to worry about that, right? What are ways to avoid this or mitigate this is you should raise the price to avoid this wild goose chase, right? And so there's a proposition that goes with this. If you have a certain price at which the largest equilibrium is in a wild goose chase, there exists a higher price that brings the equilibrium out of the wild goose chase situation into a good outcome, right? So, so this is a pricing solution, and I mean, I guess the key here in this model, I mean, it's in any model, if you're at the wrong price, right, then you should adjust the price to do better. But here, if you're in a wild goose chase region, a small price drop, right, could really have drastic revenue effects, adverse effects. Then they have a bunch of Uber data. I'm not getting into how they calibrate the model and so on and so forth, but just to sort of show you, and let me maybe focus in the interest of time just on the left figure, right? Is you can see here, think of this as the completed trips, right? And the ETA or the pickup times, right? And these are different quintiles of supply levels of drivers. So these are not queues as in quantity of trips, but think of different L levels in the theoretical picture, right? And you can see that a lot of these supply curves have, sort of this backward bend. That's kind of the main thing here, right? There's a lot of other things. I may not get into, the other figure because I want to make sure we get soon to the other models for today. So then, a pricing remedy for the wild goose chase. And so now what they looked at is they calibrated their model with Uber data, right? And they looked at this in great detail. I'm just showing you sort of a quick high-level highlight here, where they said, okay, over the course of the day, right, you have the market in different sort of regimes, right? High demand regimes, lower demand regimes, right? What they call here strong market and weak market. So this could be like, late morning is the weaker market, strong market is, in the evening rush hour, right? And in each case, we're showing performance, and here is done for welfare, but it would be similar for revenue, is as a function of price, right? So this would be the optimal price, about 6 point, something, and these are normalized prices. Think of like a surge multiplier. And this would be the price in the strong market, right? And you can see that in both cases, if you're just a little bit lower, right? I mean, if you're just a little bit lower, it's fine. But if you just are a little bit more than that, right, things are really collapsing in terms of welfare, right? Then they also look at what would happen, if you wanted to set a uniform price. And so this would be, think of it like the price that is optimal as a time average for the strong and the weak market, right? And what you see here is that that price is a lot closer to the high market price than to the low market price, just because there's not much leeway to price much lower, right? If you price lower, you're really going to harm performance very dramatically for the strong market. On the other hand, notice that even though you're pricing too high for the weak market, right, the welfare drop is very small. I think if you look at the numbers, it's like 3 or 4%, right? And that's because of this asymmetry, right? In one case, in the strong market, if you went below that uniform price by a little bit, right, you would collapse into this wild goose chase equilibrium. Whereas for the weak market, you're kind of on the safe side where things are not that drastic, right? So this is kind of a pricing solution to this. And they sort of propose that, whether you actually do time dependent based on market regime or you average it, right, you want to make sure that you avoid this wild goose chase. Another remedy, which is an operational remedy for the wild goose chases, is to say, well, wait a second. I mean, this matching protocol, if you recall what we discussed last time, right? That matching protocol was based on first dispatch, right? So a request is generated and this customer is going to be matched to the closest driver, even if that driver is quite far away, right? And it's going to be a commitment and it's irrevocable. And so, of course, there's kind of this negative feedback loop where if I have fewer drivers, right, I get a driver that is far away, right? That's going to eat up a lot more capacity and so on and so forth, right? So a natural thing is to say, okay, once you start running low on available drivers, right, eliminate this immediate matching rule, right? Be a bit more flexible, right? Then they do an analysis. Again, in the interest of time, I'm not going to go into the details, but the bottom line is that you want to basically have matching protocols that once you start running out of drivers, right, they basically stop having immediate dispatch for everybody, right? And they discuss various implementations, and those are pretty close to what is done in practice, where you basically have a dispatch radius that is a maximum dispatch radius. And there's 3 variations on how this might work. One is to just say, okay, if a customer request comes in and the nearest driver is outside this maximum dispatch radius, you just deny the trip, right? Now, it's possible that they might come back and re-request a trip or retry a bit later. Another one is to say, if riders are willing to wait in queue until they're matched, right, then you can say, okay, I'm going to put you in a queue until the distance to the nearest available driver is less than the maximum dispatch radius. Of course, that requires customers being comfortable with that idea that they're waiting to be matched, right? Another one is like rematching, where you just immediately match to the nearest available driver, even if that driver is outside the maximum dispatch radius, right? But then you keep track of the system, and if at a later point in time, right, that driver is still outside the maximum dispatch radius from that customer, but there's another driver that becomes available inside that radius, right, you can rematch them, right? So here's just a picture that is showing
the first matching then?
Sorry?
What's the point of the first matching? Like your
think of it as like, okay, like if in the end, if
you might still get the other guy.
You might still get the other one, right? Yeah. Right. But if something better happens, I mean, something closer comes up, right, then you can release that driver, and that driver that is still far away might be matched to somebody else, right? So what this picture is showing is saying, okay, let's set a fixed price, which is suboptimal, which puts you in a wild goose chase equilibrium, right? And, that fixed price is actually, think of it as the welfare you get at that fixed price under the first dispatch protocol is at this level here, about 78%, which is equivalent to saying, I make the maximum dispatch radius, large enough, right? You can see that welfare falls off. So under first dispatch protocol, right, the maximum dispatch radius, you can think of it as it's just infinite, right? And what this graph is showing, again, for some of that data, it's saying, okay, what percentage of optimal welfare is achieved under these variations of how we use a maximum dispatch radius protocol. And you can see that, there's a range. First of all, as long as it's dotted here, right, you're still in a wild goose chase equilibrium, even with the maximum dispatch. And then there's this kind of, favorable zone where the dispatch radius is short enough that you're, not in a wild goose chase equilibrium, right? But then, of course, if it gets too short, right, then, response time gets large for customers and welfare suffers again as a result, right? So, too much denying or waiting can be detrimental for welfare, right? Now, in terms of rematching, if you have a low enough maximum dispatch radius, then every rider request is going to get this mismatched. And the final thing is that search pricing is still, like, the optimal pricing, right, is still going to dominate all these options, right? You never get to 100% of optimum, right? I mean, in practice, I think what's being done is a combination of more clever matching and still having some price flexibility, right? So there's a lot more one can say about this model. So conclusions here is a parsimonious model of on-demand platform with spatial friction under balanced demand, right? And results are here on the key roles of pricing and matching to mitigate these spatial inefficiencies, in particular, the pickup times becoming very long, eating into your capacity and giving you this vicious cycle, right? Some further reading, some of these spatial queuing models go back to, before the 80s. Larson and O'Doney is like a book on urban operations research that has some nice treatments of some of these models. There's some dynamic vehicle routing, some classic papers by Bertsimus and Van Ryzen. Jan et al. Has a review of matching and pricing, and a sort of pool matching mechanism that is also using some of these ideas of weighting and matching and adjusting things over time, again, to sort of mitigate the long inefficiencies of detours and idle vehicles moving. And then Bespes et al. Have a spatial capacity planning model that is using a near optimal dispatch rule that is inspired by this paper here. And then, once we start talking about instant matching versus delayed matching, right, that then also gives different delays for customers that choose one option versus the other, right? So you have price discrimination, you have service discrimination with this spatial aspect. So there's a recent working paper by Freund and Van Ryzen that sort of combine this model with this delayed matching option and add on top of it a price discrimination angle, right? So here the idea is that customers that you can put in a queue before you match them, there's going to be then a pool of customers for whom you can do some sort of more clever matching, and you can sort of figure out how to match among them, and that will presumably improve your supply rate, right? So you get some more scale economies in dispatch. Further thoughts, this model here is has no structural demand imbalances. So interesting, non-trivial, but interesting might be to look at demand imbalances. And then at some point I looked at, with some colleagues, at public transit, and there you have things other than efficiency or profit maximization, but you might have fairness considerations for heterogeneous regions within a city. So that raises questions of how to allocate capacity across different regions and how to sort of equalize or reduce the variation in terms of fairness, in terms of pickup times and or prices and so on. And models like this can also be helpful because they're very parsimonious to do these higher level optimizations. Right? Okay, so that's part one, the end, I guess. Any questions? All right, so let me go back then to part two, right? So you can see we already went a little bit into this area here, right? So I will focus on decentralized supply control with multiple locations. And the important thing is we have spatial demand imbalances, right? That are not just because of stochastic fluctuations, but are in some sense structural imbalances, right? Now, before I look at the decentralized world, let me take a quick look at the centralized world, right? So there's quite a few papers there. And I think it's still far from exhausted what one can do there. And again, I apologize if I'm forgetting. This is not meant to be exhaustive, right? I try to kind of list what I just came to mind. I double checked a little bit. And here I just basically just to slice and dice the space here. I thought, okay, let's first briefly talk about centralized control, and then the discussion is going to focus more on decentralized control with this kind of as a reference point, right? So when we're thinking of pricing, it's basically pricing is your only tool to manage any potential demand imbalances in the network. In other words, in the pricing models, right, at least in their purest form, right, no vehicle is moving empty, right? The only thing you're trying to do is you're trying to see, okay, I regulate the flow of demand and therefore the flow of vehicles in the network, right? So there's a bunch of papers here. Some are looking at static policies, others are looking at dynamic policies. And then there's various bounds on how well a static policy can do, compared to an optimal policy, right? Repositioning is, and we'll talk about this more in detail, is you're really, so this is different from dispatch, right? Dispatch matching, what we talked about before, is there is a request here, but the car, there's no car right here. The cars may be here, there's another one here, there's another one here, right? I am reacting to this request and I'm moving the car. Repositioning is different, and it's particularly important when you have structural demand imbalances, which is, oh, there's a lot of demand here, right? Going from here to here. And so there's a lot of cars ending up here, but there's less demand going from here to here. So now you have two options to balance the network, right? One is you just reject, you just have to give up on a lot of demand that is coming from the high demand location, or you can say I will move empty cars, deliberately back to the high demand location, right? And this is done not necessarily, in anticipation. This is done in anticipation of requests, right? Before requests come up, because you know that the rate of these requests is higher at a certain location, right? So here, there's again several papers. I'm going to spend a little bit of time talking a bit about this one here. So this is kind of static repositioning. sort of showing a nice work that sort of motivates the use of a fluid-based policy. And then these are dynamic repositioning policies. There's just not enough time to talk about everything, right? But I'm just giving you some of the highlights or some of the, roadmap indicators, right? Then there's matching papers where, again, things are done in response to requests, right? Those models are quite different, right? So Feng et al., for example, is things are moving in a circle. I mean, it's like a circular city, and they basically do performance analysis. If you have like street hailing versus, you can just call or use an app to hail a car, and it's a sort of a nice classic queuing analysis, but for a circular world. This is more like a multi-location network with matching policies. These are open networks where actually there's more like a cost of going to another location more than time. Matching and repositioning is done. There could be other papers. The one I'm aware of is by Atta et al., right? And then there's capacity planning models. Base space I mentioned before, that's kind of in this continuous space world. And then the other ones are in this kind of discrete network with multiple, nodes and links in between the nodes that are basically travels or trips, right? Now, one thing, once you look at these papers, right, and I think that's in the context of this mini micro session, right? I think it's helpful to talk a little bit about, even though there's lots of different models, one modeling framework that comes up quite repeatedly in this world is one of closed queuing networks, right? So what I thought I would do before I talk about, my work with decentralized control, spend a few minutes to just highlight a few things from the closed queuing network world, which is fascinating and quite deep, right? I mean, I'm just going to sort of not even get to the highlights, right? But just a couple of observations, right? So first of all, what is a closed queuing network, and what is its, this kind of framework? How does it work in application to ride hailing, right? So as the name suggests, in a closed queuing network, the number of circulating jobs or units is fixed, right? Constant at some number. It could be any number, but the idea is that that number stays fixed, right? Now, the traditional motivation, or at least one key motivation that I'm aware of, is when you have a multi-stage production system with constant work in process, right? Sometimes called conwit system. So think of it as, we don't want to flood the process with a lot of extra work in process. So we set a certain work in process level, and then a new job is started if and only when another job, let's say of the same class, has been completed, right? So each production station is characterized by a number of servers. There could also be transits that takes time between stations. So that could be transit stations. And then each job class is characterized by a routing sequence through these servers, right? And a service time distribution at each station, right? And then, of course, we can also talk about priority, discipline at each station, and so on and so forth, right? Now, how, at least all of the papers, if I'm not mistaken, not all the papers on the previous slide use a closed queuing network, but those that do, I think, share more or less the following features, right? You have a fixed number of locations or regions. Let me call it R for now. There's a fixed number of cars or job units. And, similar things have been looked at where the motivating example is like a bike sharing network, right? And they circulate in the network, right? Now, in this thing, in this world, the customers are the servers, right? Because they show up and they trigger car movement upon arrival, right? And all of the networks, like all of the papers that I'm aware of, I think, assume that the customers do not wait if no car is available, right? So that simplifies the state space. So on the customer side, you have like a loss network, right? And think of it as customers are like extremely impatient, right? Or extremely time sensitive. And so the network has really two types of queues or stations, right? Single server pickup queues, right? One at each location. And the queuing items are the cars or the drivers. It's not the customers, right? And infinite server transit queues or stations. This is like their travel, that captures the travel of cars from one location to another, right? And so a pickup queue is associated with each location, and the service rate is basically the demand rate. Now, typically, I think all the networks I've seen, assume Poisson arrivals, right? So basically, even if you start with an idle station, right, there could have been arrivals that showed up, they didn't find anyone, they disappeared again, right? As soon as a car arrives, they would typically arrive to, there's no passenger there, but then the residual service time is again exponential because of the memoryless property of the Poisson process. And, the service rate is basically the arrival rate of the customer. In the pricing or admission control papers, right, that arrival rate can be regulated. Otherwise, it's just a fixed quantity that's given, right? And the transit queues are associated with transit from location I to J, and the service times are simply the trip times, right? And because unless we're assuming some sort of limited capacity on the road, right? See, these are just infinite server queues, right? Where there could be cars in parallel, right? And then the routing, the accepted demand is basically giving you the full car routing. And then on top of that, you could do your own sort of repositioning control, which is going to give you the empty car routing, right? This is just a quick picture here, right? With, two locations where we have cars waiting in the pickup queue, right? If a passenger arrives, they take a car, right? The time between passenger arrivals here is governed by the arrival process of demand, right? And then the routing, so depending on how we model locations, there could be trips that are going to terminate in the same location, in which case the car goes back here, or, maybe the car is going to, the passenger wants to go to location J. There might be other cars going from I to J. So you have your infinite server transit queue and so on and so forth, right? So that's kind of the basic idea.
Philipp, just quick question.
Yeah.
So is this assuming that always drivers don't stop working?
Oh, so I mean, here, this is, so in this model, I guess in the strict interpretation of the closed queuing network, right? Every car in the network is basically 100% available, right? I guess you could, I don't know where your question is going. I can think of two scenarios at least to modify that, right? You could say, okay, we have an additional node where, they go and take a sandwich or something, right? Or that could be fun to look at, right? Like, so like a server vacation that, like in the classic queuing parlance, right? So I'm not sure whether I've seen such models in this world, but that's certainly a possibility. I don't know, is that where you're going?
Yeah,
right?
It doesn't need to be a sandwich. It could be for
We're not going to impinge on the privacy of the drivers. Who knows what they're up to, right? Yeah. And then you could it could also be sort of, they could also have, we can think of lots of things. They could probabilistically also leave the network and whatnot. And so it could be not purely closed, but it could be open as well, right?
I mean, the first one will remain a closed queue. Right?
Yeah, absolutely. Yeah. Right. Yeah.
The only difference is the rate at which this queue is not is not anymore, because the service time there is the 1 over lambda, if lambda is the arrival rate of customers, while this one will have a different rate. Right?
Yeah, but I mean, it could be, you could associate it. There could be different classes of drivers, and they have different, needs to break, or I mean, it could be anything. It could just be any time that they're not available for this. Like, maybe they're students and they do some other work, right?
So you're thinking control, because one is controlled by the price to the customer, the other one will be controlled by the wage to the driver, right? So to some extent, right? So,
yeah, that's true. Yeah. So I mean, I think even the quote unquote simplest model is quite rich, and you can certainly add all kinds of bells and whistles, or at least consider it, right? Okay, so I thought, just there's no, I cannot even begin to do justice to all the analysis and, results that are out there, but I thought I would just summarize, if this is of interest for this audience, a few key things, and then, you can do a lot of fun reading in this literature, right? So just a couple of quick, and it was actually fun for me to revisit some of these papers also. Right, so like, what are some of the performance metrics we might care about, right? So the stationary queue length distribution, the mean queue lengths, the idle times. And then this would be important for, like, especially when we have customers that are not willing to wait, right? You want to know what's the probability that there's actually cars at a location, because otherwise you're going to lose demand, right? And so this enters the objective function in various papers, like the pricing papers, the admission control papers, the repositioning papers, right? Like, if I just care about some weighted sum of throughputs, right, and the weights could be prices or something, right, this would be an important measure for me, right? Now, there's an important class of networks that could be actually open or closed. And there's this classic paper in 75. And according to the authors, these networks are known widely as BCMP networks, right? Finite number of queues and finite number of job classes. One important assumption is that the routing is state independent, right? So it's basically, think of it as there's a transition probability matrix, but that matrix does not depend on how many customers do you have where at what time, or how many drivers rather, right? There's a variety of assumptions on how the service station operates and what the service times are that give you criteria for, is the network a BCMP network or not, right? And this is not just in ride hailing, right? This is 1975. I'm not sure to what extent they were thinking of ride hailing back then, right? But so in our world, if you're thinking of the pickup queues, right, with Poisson arrivals, that would be satisfied. Infinite servers, that would work for the transit queues. And there's some other possibilities, right? And for types 2 to 4, actually, you don't need exponential service times. Anything with a rational Laplace transform would still work, right? Now, if you have open networks, as opposed to what we have here, right, then some state-dependent Poisson arrival, some specific type of state dependence would qualify, right? The key result, or a key result for such networks, is that the stationary queue length distribution has product form. And I went back to the original paper. And so basically the product form is, if we have n stations here, so this is just different notation. So this is not n cars, this is n stations. Think of R regions, right? The joint probability of the number of cars in the different locations has product form, and these factors here the argument for each factor only depends on parameters of that station. So it's sometimes people say as if the station was operating in isolation. Now, to figure out what the function is, right, you need to solve some balance equations to see what is the throughput and what is the service rate and so on at the station. But, this can be done. The difficulty is this normalization constant, because essentially you need to figure, it's just like when you do some simple single server queuing analysis, the normalization constant is there, and you need to make sure that these masses sum up to 1, right? And so if you want to use this as an input to your model, the challenge is, first of all, for closed networks, computing this constant is computationally expensive. But then also, if you want to run an optimization problem, it's not very suitable. Certainly, it's not very suitable to get any sort of structural results or something, right? If you want to just compute it and brute force optimization, it might work, but it's that's a big drawback. Even though you can efficiently compute it, it's unsuitable as an input to the optimization, right? Another approach is to say, look, maybe I don't actually need to know the stationary distribution, right? I just care about averages, right? Average throughput, average queue length, average waiting time, and so on. And another key approach is leveraging the so-called random observer property that holds in a BCMP network, which states that an arrival to any queue in a network with, let's say, n items observes the stationary distribution of an identical network that has 1 item less, right? So think of it like the 1 item that's arriving, there's n minus 1 left in the system, but you still need these properties to actually make sure that in steady state, it observes the stationary distribution that would be there if it was an otherwise identical network with 1 less item in the closed network. And this goes back to a classic paper by Reiser and Lavenberg. And so mean value analysis is well known in these closed queuing networks. There's also an approximate mean value analysis if these assumptions are not exactly satisfied, right? Okay, so then I sort of went back to these papers here, right? I was just curious. And I said, okay, so, of course, I didn't look at each and every paper, but I just thought, what are some of the things that we see in the analysis, right? And it definitely made me curious to read these papers in more detail, right? So just, some approaches, right? So Ben Jafar has a couple of papers that use mean value analysis in an elegant way to develop bounds and approximations for the throughput of a network, right? And they use these bounds and iteration on these bounds and approximations to figure out a fleet sizing problem. Basically, how many cars do I need to achieve a service level of at least X% everywhere, right? And then more recently, also a pricing problem that allows you to say, okay, the static optimal policy gives, it performs at least as well by this percentage as the best state-dependent policy, right? So, there's subtle things here that I was tempted to try and elaborate, but I would be even more out of time, right? So this is exact analysis, right? And then there's a couple of asymptotic analysis approaches, right? Where you say, okay, let's let something go large. One regime is what sometimes is referred to as the infinite supply regime. As the number suggests, is let the number of items go to infinity, holding the service rates constant, right? And Banerjee et al. Is an example of that. There's a lot going on in that paper, but that's one sort of feature of the analysis. And then if you do this infinite supply regime, first you get the stationary distribution of the limiting system. And if you look at the relationship between that system and the stationary distribution of finite systems, you can exploit that to get some bounds on how well a static policy would perform, right? So sometimes some people say, well, but I mean, you really need to have a lot of vehicles for this to make sense, and you're still keeping fixed the number of locations and so on and so forth, right? Another regime is to say, let's look at a so-called large market regime where we're scaling the number of vehicles and the demand rates proportionally, holding constant the service rates. And this is the paper by Braverman et al. They look at repositioning. And they basically show that if you scale the number of vehicles and the arrival rates, you get they establish convergence of the stochastic system to a fluid limit. They then show that if you look at the fluid-based optimization problem, the static policy that is fluid optimal gives you an upper bound on the utility under any routing policy in the stochastic system. And this fluid-based static, fluid optimal static policy achieves this upper bound asymptotically, right, when the system gets large. So this is kind of in a nutshell. Now, I was foolish enough to say, you know what, let me put some details here. I'm just going to show you this very quickly, and then if you want to look at these in the slides or even better in the paper, you're welcome to do that. So this is not meant to be a serious treatment, but I thought it's kind of fun to sort of think of this. So the model here is you have a fixed number of locations. You have n vehicles, and you have customers arriving according to some arrival rate, which is scaled by n, right? Demand is lost if there's no vehicle available at the origin location. There's a fixed destination routing matrix. So think of lambda ij's that are sort of exogenous. Travel times are exponentially distributed with the rate vector mu. And the decision variable is an empty car routing matrix, right? So the idea is to, control the flow of empty cars to try to get as much utilization weighted by the rewards of the different requests, right? So that's basically the problem. Select empty car routing matrix to maximize some concave utility function of the weighted.
So Philip, sorry again, this means that by definition, the control is a static control.
They
from the start, not
at the beginning. No, up front they don't restrict to static. What they do is they show that the system under any they show that the fluid-based optimal policy, which is static, is asymptotically optimal and so on, and it outperforms other non-static policies, state-dependent policies. But they don't do like let's say a first principle analysis of a state-dependent routing policy, right? They just bound the performance. So, I mean, at the risk of oversimplifying, like some of the earlier sessions that looked at fluid policies and said that, look, the fluid gives you an upper bound. In some sense, you have that parallel, yeah. Does that make sense?
Yeah.
Right. Okay. So, so the key performance metric here is going to be the availability at station I, is basically, what's the probability I have that the number of cars at location I is bigger than 0. They first do a nice illustration of the exact analysis is like the computation for the fixed policy is one thing, but then the problem even for 2 locations is non-convex in these, repositioning probabilities. And so what they do is they do a large market regime, right? So, and I'm just going to blow through this in a few slides just to give you, so think of it as the original continuous time Markov chain in a system with n cars is basically characterized by these 2 processes, empty cars full cars. And the superscript n is just, think of in the n system with n cars, right? You can then do the fluid scaling of these Markov chains. You just divide by n, right? The routing matrix, a priori could be state dependent, right? And it's going to show up in in one of the main results that you could pick any routing matrix, but there's just going to be a bound on the performance under such a policy is upper bounded by the fluid optimal static routing policy, right? So then think of the argument infinity for the t as basically a random vector with a stationary distribution of the fluid scaled continuous Markov chain, right? And this would be similarly just the shorthand for the availability in region I, right? Here, just to illustrate, if you were to do exact analysis in system N, right, it would have this type of flavor where you start to look at the transition rates and you're trying to calculate the steady state probability and so on, right? But they don't really go into this, right? Instead, they present a fluid-based optimization problem. And here, I'm not going to go through all the details, but think of here, basically, these are, the Q is a static routing probability matrix, right, which is ultimately the decision variable. And before you had capital E for empty cars and capital F for full cars. These are now all normalized by N, right? So these are fractions of empty cars. That's a matrix. Fractions of full cars, right? These are all, deterministic variables. And then the availability in region I, again, a number between, 0 and 1, right? So this is the, here, these are the rewards. So this is the simplest version of the objective function. You want to maximize basically if these are revenues, right, then this would be the revenue rate. Lambda I is the exogenous arrival. Pij is giving you the effective, this is giving you the exogenous arrival rate that goes from I to j. AI bar is giving you the acceptance probability. So this gives you the effective rate, right? And you want to maximize this thing. Subject to what? There's various sort of balance type of, conservation of flows or inventories. The full cars have to satisfy Little's law, the empty cars, right? Then there's flow balance in the regions in steady state, right? You have to have these flows match, right? And then if you sum up all the empty and the full cars, right, because it's normalized, they have to sum up to 1. And, the usual sort of non-negativity constraints and so on and so forth, right? And the main results are essentially these two theorems, right? So the first one is saying, okay, pick a feasible solution to the optimization problem, the fluid optimal problem, right? Then implement this static routing policy in the stochastic system, the continuous time Markov chain, right? And then basically what you have is you have the steady state capacity distribution or Q-length distribution weakly converges to the fluid equilibrium capacity distribution, right? These numbers here. Excuse me?
The fixed point.
Yeah, right. So that's for any feasible solution to the optimization problem, right? And then you can say, okay, now suppose you pick, the fluid scale, this continuous time Markov chain. Under any routing policy, Q could be state dependent, right? And you say, okay, what will be the performance in the continuous time Markov chain, right? For any fixed n, right? That's lower bounded by the utility or revenue rate or whatever you want to call it under the fluid optimal solution, basically the optimal n optimal solution to the fluid based model over there, right? And then furthermore, if you were to run the static fluid-based optimal policy, right, and if you let n go to infinity, right, so in the large market, in the large market regime asymptotically, right, you can actually achieve this bound, right? So this is kind of in a nutshell. And again, like, you know, if you want to read the proofs, it's going to be fun. It's like a 40, 50 page appendix. There's lots of subtleties here. In case you care, you know, here, so the building blocks for theorem 1, and those are, I think, you know, classic steps. And to be sure, I'm not an expert in this type of analysis. I enjoy reading it, but I have not focused on that type of analysis in my work, right? But there's sort of one part which is process level convergence to the fluid model, right? So the fluid model is basically described by a set of ODEs, right? And you show that the fluid scale processes, you know, converge almost surely to the solution of this ODE. And then the second point, and this is in this paper, the main technical contribution as articulated by the authors, is to characterize the equilibrium point of the fluid model, right? And basically the equilibrium point of the fluid model under a given static policy, you know, they will satisfy these constraints that you've seen in the fluid-based optimization problem, right? So this is, you know, a very, very high-level overview. But I thought since this is sort of stochastic modeling, I would, you know, do a little detour on those things. And it's fun reading, and I think helpful tools if you ever think of either doing this kind of analysis or using it in other models. Okay, so I think I have 25 minutes left, but that's okay. So now up to this point, I was, you know, I was just operating in this box, right? And I'm going to basically, what I'm going to do is I'm going to take a special case in terms of locations of the model considered by Braverman et al. But I'm going to add some complications because the drivers are making their own decisions. Those include, should they join the network or not? So for any given n, there's going to be, if they join the network, they can decide whether to reposition or not. That's going to induce a profit rate, and then this profit rate is going to decide, okay, did they actually want to join the network or not? So there's some complication to that. There's some complication through decentralized repositioning. And then we also allow the platform to do admission control, not pricing, but admission control, which basically means that I can discriminate between two types of demand arriving to the same location. Whereas in the Braverman et al. Model, at least in the model that they studied, right, at any given location, you would have the same availability. Think of these AI bars that we looked at. They're the same for all trips that are originating there. Whereas here we're allowing to discriminate based on, let's say, destination, right? So, and I mean, I already know that there's no way I will get to this, but, you know, it's there just in case there had been time, right? So it's a stationary model with imbalance. And we're going to look at admission control and the interplay with repositioning, especially when repositioning is decentralized, right? So when you have strategic drivers, right, depending on how you run the system, what is the sort of equilibrium distribution of cars and you know, how you're doing in terms of revenue and so on. And we're going to look at a couple of different regimes depending on what operational controls you're using. Demand admission, so think of FIFO or basically non-discriminatory, that's what you saw in the Braverman paper, versus optimal when I can discriminate. And on the supply side, the obvious question is what happens when you decentralize those decisions as opposed to having autonomous vehicles or drivers following orders, right? So so a key thing here that comes out of this analysis is that there's under decentralized repositioning, right, there's obviously going to be wasteful queuing because drivers are trading off wasting time through traveling and wasting time through queuing at a low demand location. And so unless their idle time is long enough, they will be reluctant to reposition, right? Admission control can somewhat mitigate these losses. And one thing that comes out of this, which I think, at least to my knowledge, is of a novel role of admission control in this setting, which is that you can use it to in some sense manipulate the incentives, the repositioning incentives of strategic drivers, right? We call this demand rejection. That might be optimal to induce repositioning to the high demand location, right?
But the wasteful queuing comes from the fact that customers also are lost because if there are no matching with the driver.
Because I mean, yeah, I mean, I guess it's amplified, maybe, right? I mean, I think like if yeah, right. I mean, by definition, you cannot have customer queues, right? I think if customers could queue, that they would still happen if you have an excess, like, if the demand rate of customers is low relative to the supply rate, right?
Oh, sorry, what I meant is that when you're talking about wasteful, is really what you care as a platform still from a are you introducing objective the cost of waiting of the driver, or is there a utility function that is
yeah, fair enough. Like the I guess you're right. If that would help reduce response time for customers that are still coming, right? It might be interesting to see how much. Yeah. Let me show you what I mean by wasteful here. And I think even if you have customers queuing, there would still be, drivers would still be wasting more time in the wrong location sometimes compared to the case where you can just tell them what to do. So, then what we also do is we look at we get some upper bounds on how much you gain from, controlling the system as opposed to having decentralized control. And that gives us some tension between the two. Okay, so I think in the interest of time, I'm just going to sort of blow through the problem formulation and highlight the things that are new here relative to the model you saw earlier, right? So, one thing that really complicates the analysis here is the fact that drivers are strategic, and this goes back to Ran's question from last time at the very beginning, what's the time scale? And, the drivers in this system, they're long-lived in some sense, right? They don't just compute their utility for one transaction, right? So they need, unless we think they're myopic, right? They're really anticipating what's going to happen in the system, and what's going to happen in the system now depends on the routing, both of demand and on what other people do and the queue lengths and so on, right? And so this extra constraint that governs drivers, both their behavior in terms of whether they join, and second, if they join, how they choose to reposition or not, right? It adds a significant complication to the model. So in any case, so and just to be clear here, we're just starting with a fluid model, right? So we're not doing a Braverman style analysis to justify the fluid model. That might be an interesting exercise, but that's not what we do. right? We say, okay, let's assume we have a fluid model. I think the fluid model makes sense and it looks similar to the model they study, except we have these additional things. But we have this fluid model. Now, what do we do with it, right? So you have a potential demand vector of capital lambda. Customers are impatient, right? Each ij, and so here you have basically 4 routes. For each route, we have a constant travel time, potential demand rate. The only assumption, which is without loss of generality, think of location 2 as high demand, right? On the driver side, it looks similar to the models we looked at last time, right? There's a driver pool. There's now here, because they're moving and that costs money, there's a driving cost rate, which we assume to be identical. And then there's an opportunity cost, which comes from some distribution and which the platform doesn't observe. So once a driver is in the system, drivers are identical. I think Ron here has a paper with Costis and Jim Dye, right, where you assume that this, what if this is actually known and could be used this to discriminate or to prioritize drivers and so on, right? The price is fixed per unit time and there's a fixed commission rate, right? And so it's really just about how to regulate the system, right? So if you start to look at each location, you know, these are sort of the outside arrival rate request, demand rate requests coming in. And admission control in the fluid model is simply going to translate into little lambdas, right? Queues of empty idling cars, they're matched FIFO to demand. Again, these drivers are indistinguishable to us once they're in the network. And we assume that they accept all the rides. And repositioning control could be done by the drivers in the decentralized regime or by the platform in the centralized regime, right? We can think of it in 2 equivalent ways, so to speak. Flow rates at the aggregate level, at the level of an individual driver, they're sort of think of it as a mixed strategy where they randomize whether they reposition or not, right? If they never reposition, then eta 1 is basically 0 and they always join. If they always reposition, eta is 1 and they never join location 1 when they're empty, when they drop off a passenger, and eta in between is playing a mixed strategy, right? And when the drivers make this decision, they're basically trading off idling, you know, versus repositioning. Then, you know, the flows that enter this queue are basically, you know, people who reposition from 2 to 1 plus, you know, demand that is terminating in location 1. Notice that in this model, there will only ever be repositioning from the low demand to the high demand location, right? This is when you put the network together, right? You basically see that we looked at location 1, location 2 has, you know, this kind of symmetric. We have the flows here, and you would have sort of very intuitive constraints, flow balance, where, you know, the sum of demand from 1 to 2 plus repositioning flows from 1 to 2 has to equal the sum of the flows in the opposite direction. And the capacity allocation is basically between service and repositioning and queuing, right? So it's basically, you know, how you're going to allocate the cars, right?
Philipp, the problem is this similar complexity if they have more than 2 locations.
So I have the difficulty with more than 2 locations is only when you have the drivers making the decision. Because now, you know, you can, so basically from a driver's perspective, they're basically sort of figuring out, okay, how should I route myself through this network, right? With more than 2 locations, you have, you know, you have all kinds of possibilities. And so basically, we have, you know, we just resubmitted the revision a month ago or so. so we have the problem formulation in the general case, right? It's just, think of it as basically at each location, like, here we have two locations. At each location, I have two options, whether to join the queue or not, right? When you have n locations or r locations, right? At each location, you have r options, right? To have equilibrium, right? Yeah. So long story short, it significantly complicates the problem. Okay, so the platform is going to maximize its revenue, right? So basically so here this eta is basically has just two elements, right? What do I do at location 1, which is a binary thing, and at location 2? And the average profit rate has this flavor of the sort of renewal reward theorem, right? Where it's like the length of a cycle in the denominator, the reward per cycle in the numerator. And of course, these things I'm not showing here, but you need to make sure that those are actually correct given the waiting times and the demand mix and so on, right? So on the decentralized repositioning, drivers choose eta symmetrically to maximize their profit, and then the drivers will participate if their opportunity cost is less than or equal to the equilibrium profit rate, right? Just from a gaming perspective, information requirements, the platform knows the model primitives, and the drivers need to know, basically the demand mix, which governs their routing probabilities when they carry a passenger. And they also need to know the delay at each location plus the travel times, right? And so we look at, as a benchmark, centralized control, which is, as the name suggests, right, the platform is going to choose based on destination and everything, how to admit customers, and it can choose how to route the empty cars, right? Minimal control would be, in some sense, FIFO admission control is think of it as pretty much what you have in the Braverman paper. But then here with decentralized control of repositioning. And admission control is kind of something in between, which seems plausible. The drivers decide what to do in terms of where to go, but the platform regulates the demand that is admitted, right? Since we talked about the fluid model in the Braverman paper, right? Like, again, we did not do this analysis, but what it would entail is essentially you have these additional equilibrium constraints that need to hold, right? So one way to maybe approach this, but just to be clear, we haven't done this, is to say, okay, fix a policy, right? Then look at the usual things, right? The convergence to the fluid model, the fluid model having a steady state, an equilibrium point, right? And then you would need to check in addition that for sufficiently large n, the driver equilibrium strategies are actually, incentive compatible. Like what you want them to do is consistent with their objective, right? If that's the case, you need to sort of calculate, what is approximately at least their profit rate, right? And you need to make sure that their participation is satisfied, right? So, I mean, this could be a fun technical exercise, but we did not attempt this. But yeah, right? Okay, so then what we do in a nutshell is we analyze the system under each regime for a fixed capacity n. We do this in terms of a capacity allocation problem. And then, given the n, you get an equilibrium allocation, a driver profit, and then you determine that there's an equilibrium participation level, right? Let me I think we have 6 minutes. So I'm just going to cover the key points so the first thing is what you see, and you'll see 2 more pictures like this. On the horizontal axis is the capacity in the system. So think of closed queuing network with n units circulating, right? And what you see on the vertical axis is the allocation. So as we go from small n to large n, basically you have more and more capacity. In zone 1, you have basically scarce capacity. Drivers are fully utilized serving passengers, right? At this point here, you serve all the balanced demand. And then you say, well, now I need to do some repositioning, otherwise I cannot serve the excess cross-location demand, right? But so basically, you then just direct drivers to reposition, right? And queuing only comes in. Notice here that the demand served is leveling out, right? So basically, we don't need any queuing until all the demand is served. So this is good. Obviously some sort of as efficient use of driver capacity as possible. Of course, if you had balanced demand, you could at least in the fluid model serve all the demand without any repositioning or queue, right? Okay. So then there's decentralized repositioning. So there's I have a detour here. Long story short is for drivers to reposition, right? They're asking themselves this question at location 1. Why? Because there's more flow going from 2 to 1. So they tend to accumulate at location 1. And, they basically ask themselves, should I stay or should I go? I think there's an old song that is not about this, right? And basically their trade-off is, if I go, I'm going to drive empty and it's going to cost me time and money. If I stay, I'm going to wait here and I'm not going to make any money, right? So as long as the queue, I need the queue at location 1 to be long enough for me to have an incentive to relocate. And that's what I meant by wasteful queuing. Right now, one can enrich the story, but that's basically the idea here, right? So this is, and now the interesting thing here is that once you do the analysis, there's going to be an indifference threshold. And this indifference threshold really captures a lot of the fundamental features of the problem. What is the mix of admitted demand at both locations? What are the travel times? What are the financial parameters, right? And so just to foreshadow this thing that I said earlier, when you execute admission control, you can do this in a way to reduce this indifference threshold to push drivers to reposition. The expense of that is that you're losing demand at this location, but you may more than benefit, you may offset this by having drivers go and get more of the high demand at the location 2. This is sort of the formal characterization of a repositioning equilibrium for a fixed amount of capacity, right? Now we have 2 scenarios where with decentralized repositioning. One, which is, again, no really admission control. And you have basically 2 inefficiencies, right? One is, notice that unlike the earlier picture you saw, queues start to build up before we serve all the demand. And the reason is precisely what we discussed on the previous slide, right? But then because you don't do destination, you don't exploit destination information for admission control, right? There's actually an extra inefficiency, which is that you're losing, so there's inefficient driver utilization. First, the drivers queue at low demand location 1, right? Meanwhile, you're still losing demand at high demand location 2, but you're losing actually 2 kinds of demand, right? You're also losing some of the local demand at the high demand location, right? Why? Because you're not able to discriminate based on destination. If you could, you would say, if you're actually staying in the region, I'm going to preferentially give you access, and that will keep the cars in this location, right? So that is the more subtle effect of not doing admission control. The obvious one is that you're sending a lot of flow to location 1, and these cars are only going to come back if the queue there is long enough, right? Also, just as a reference point, this is the capacity I need under centralized control to serve all the demand, right? Whereas here, I mean, this is just an illustration, but I need almost, I probably need about twice as much capacity to be able to serve all the demand, because this queuing is kind of, interfering with things, right? Now, under admission control, you see sort of, if you compare the pictures, so this is without admission control, this is with optimal admission control, right? First of all, this queuing zone shrinks, right? Second, we can already serve more demand without repositioning. And both of these results are the result of admission control. And then the last thing that can happen that may be optimal is that you may want to reject demand at the low demand location, and that will help you improve performance by getting more demand at the high demand location. So I think, Victor, we're probably out of time, right? But let me just fast. So there's 10 slides on the subtleties of strategic demand rejection. Let me just get to the conclusions here. We have various bounds here and so on, right? One fun thing is, once you look at this with 3 locations, now you have some interesting interactions between the locations where, there's a queue building up here because you want people to reposition elsewhere and that kind of thing. Okay, I did not realistically expect to cover all these slides. Let me just get to the conclusions on this, right? So decentralized repositioning incentives rely on wasteful queuing. Admission control somewhat mitigates these losses. And I think this is, in terms of sort of structural results, is probably the most, novel one, that, strategic demand rejection may be optimal to induce repositioning to the high demand location. And that gives you some novel role for admission control as a tool to influence drivers' repositioning decisions. Some further readings, there's a couple of papers that introduce a mixed fleet. So now you have some drivers that make decisions. Others are autonomous vehicles that, well, they're autonomous, but you control them like robots. There is some work outside a queuing context for how to use pricing to balance things. There's some welfare maximizing pricing, which has a very different flavor, but it's also interesting to look at. Then there's some more algorithmic work by some people at Lyft. And then I think, I hope that's the correct summary, Ran, right? That look in a similar model at a situation where the driver's reservation wages, so you can actually, it actually makes sense to maybe prioritize certain drivers to manipulate their earnings and get more of these drivers, and that kind of thing. There's lots of additional, so we're thinking of various additional things. The obvious one is to look at the interplay of operational and financial incentives. And there's lots of other interesting things. So I'm going to stop here. There's a whole other paper on non-stationary demand shock, but I'll skip that and just go to the end. All right.
Sorry, I'm gonna have to stop it here, but thank you so much, Philipp. Really, it's I think it's great to have all the summary of papers, beyond the main one that you also discussed. Kind of like, I mean, I learned a lot, and I'm sure others did. It's really nice also to have the references, but how they're linked to the different ones. So I know there's a lot of work that went for both of you, Florian and you, in putting this together. So thanks.
I have to say, I learned a lot, and that, I got really excited reading some of these stochastic proofs.
I'm gonna actually connect, and there's a couple of points that I want to discuss.
Yeah,
but, you will be hearing from me soon.
Yeah, there's a couple of questions, I think.
Oh, there is.
Or I thought hands up or not.
No, we're, I think, uploading.
Oh, okay, thanks. Yeah. Well, thanks for coming, guys.
It was really fruitful. Is there any chance to get copy of the presentation?
Yeah, I think Victor will force me to do that.
Exactly.
Thank you. Thank you. Thank
Yeah,
you.
the recording is going to be there, and as well as
Yeah.
the
Yeah.
Okay. Have a
Okay.
good night, everyone. Thanks
You
again,
too.
guys. Just remind whoever is basically surviving at this point with us that Friday there is a seminar on experimentation and double-sided platforms by Gabriel Weintraub. And I will send an email, of course, about that. Thanks again. Have a
Great.
good one, and see you all soon. Thank you.
Bye.
Bye.
Thank you. Bye.